So good morning. So we are very pleased to have today two of our most prominent scientists of the IPHT, the Institut de Physique Théorique at the CEA Saclay. It's Roger Balian. They are both very well known, so to introduce them, I think it's better to go on the web and look at their CV. And François David. And they have the peculiarity to be experts in quantum mechanics and to have their personal view on the subject. So today we would like to ask them the 17 questions of Maximilian Schlosshauer. Those questions were devised in 2001 in the book Elegance and Enigma, the quantum interviews. So I'd like to make an interview with our two scientists to know what is their deep view of quantum mechanics. So the first question, shall I continue?
Okay, so then, good morning. We will start with the first question, which is what first stimulated your interest in the foundations of quantum mechanics? So, Roger, maybe.
Very, very, very old question. I had to test all the exercises which were in his book. And at the same time, of course, I read the version of the book version. And in the book itself, there is a part, there are a few parts which are not very satisfactory. One part which is not satisfactory is the part about quantum measurements. It treats quantum mechanics at length in a marvelous way. However, just the part on quantum measurements, it's, as usual, just not really well treated, as in any book. And there were also a few other parts, but this was the one which just left me in a rather bad mood. And of course, since you, as any physicist, when you work, you forget about that problem. And I forgot that problem during all my career until I was old. And then I could afford to think about such a problem which is so old and not elucidated. And then it happened that Theo Nieuwenhuizen, who is here, just had recommended us one of his former students, Armen Balian, who is very good in statistical mechanics. And then I just digged out an old question, which was, let's try to understand quantum measurement by solving a model. I was not technically able to solve it really completely, so we did that together, and also together with Theo. And this is, during the last 10 years, the way we got really involved in this problem.
Thank you.
Okay.
François?
Okay, so thank you. My reason to get interested in the last 5 years, let's say, about looking at how people try to present and understand quantum physics is first teaching, because I've been teaching quantum field theory at the master level, in particular at École Normale Supérieure at the Perimeter Institute since a few years. So I started to think, how could I present not only how you use quantum mechanics and quantum field theory, but explain the principle in a sensible way. Another reason is that I've been involved in some committee selecting good projects in Brussels, and as a theoretician I got a lot of projects very interesting of people presenting quantum physics from the point of view of quantum information and having either theoretical studies or project of experiment and stating that their project would be used to build try to build a quantum computer or to do quantum cryptography or test principle of quantum mechanics, but also understand the principle of quantum mechanics better than this was done before. And I started to be a bit puzzled, and I had to learn the subject, and I wanted to learn more and to understand what was really interesting and not so. I think that was my two main reasons, apart of course from curiosity. Could elaborate more, but I think that's...
But of course you can work during all your life on quantum mechanics, which is what most people do, without digging the foundations, which is something rather dangerous because it touches philosophical questions and so on. So this people don't dare to do that.
So both of you indeed started to dig in the foundation, or have been involved in digging this foundation of quantum mechanics. So this is a perfect transition to the second
Okay,
question.
thank you.
So, what are the most pressing problems in the foundations of quantum mechanics today?
I would say
Roger.
that the most pressing question for me was to understand quantum measurements. And I think we have succeeded to do that for ideal quantum measurements. And now the most pressing problem is to understand more realistic measurements and all these new types of measurements, weak measurements and so on, which are now being performed by experimentalists, but the foundations of which are not completely settled as
Could you
well.
define maybe what you mean by weak measurement?
It's measurements in which you succeed to get, in principle, if you make a neat, clean ideal measurement, what is called an ideal measurement, you measure one quantity, but the quantities which are incompatible with them, you just lose completely the information about them. So these weak measurements are measurements in which you cheat a little, so you don't get the full information about one quantity, in such a way that you do not lose the information about another quantity, so you measure vaguely incompatible quantities together. So this is a challenge still, which has to be
I think we will have a few other questions to go back on the issue of measurement. Maybe François, what are the most pressing problems in the foundations of quantum mechanics today?
I'm a bit uneasy about this question because for me the term foundation is not very well precise.
Yes.
It's saying there is a problem in the foundation of quantum mechanics gives the impression that quantum mechanics is something that is still very poorly understood, and some aspects of it are not very well understood. But on the other hand, it's the most successful physical theory that has been, I think, devised since 2,000 years. And
yes, you can have 12 digits. A precision of 12 digits is something which is absolutely
yes. No, but not
incredible.
only that, but quantum physics has unified the whole field of physics, of chemistry, of it has application in biology. Of course, a lot of phenomena are described by just classical physics, and we are used to think in terms usually of classical terms. But for instance, I think it's striking to think that in fact quantum mechanics is more consistent than classical physics, and so which is
in what sense?
In the sense that it solves, or it gives, in my opinion, a satisfactory answer to the fact that classical physics completely neglects the retroaction and the coupling between the observation device and the physical object. In classical physics, you have a physical object, you have the observer, and you look and you at the particle and say, okay, this particle has this speed, it has this position, that's well known, and you can measure everything without disturbing what's going on. And we know from experimental evidence and now from the mathematical principles that this is not possible. It's not possible experimentally, and it's even not possible mathematically. At the logical level, you discover inconsistency, and that's this problem that quantum mechanics has solved. It has introduced new questions, but I think it's more consistent.
So this word foundations, actually, I think it's not so good.
Yes.
Because in a way, you could say just the converse. You could say that quantum mechanics is presently the foundation of all of science. Because from the reductionist way, if you accept the idea, which most scientists do, that you can reduce your theory at a lower level, quantum mechanics is below that. So from quantum mechanics you can deduce classical physics, from quantum mechanics you can deduce chemistry, from chemistry you can deduce biology and so on. And from this viewpoint, from this philosophical viewpoint, quantum mechanics is really the foundation of,
Yes, I agree.
of science. So looking at the foundations is not so new.
Yes.
So the real question is rather the interpretation of quantum mechanics. What does it mean?
Yes, and
Yes.
if I can jump in,
Perhaps I
this,
can-
this brings us to the third question actually.
Yeah,
What's the
I
interpretive
think I have
program?
not understood really to your second question. So perhaps I would say one of the
The
pressing
most-
problem is to make the subject clear for the general public. What are the real problem and what are false problem? Because one gets the impression when discussing about the foundation that quantum mechanics is poorly understood, and I think the goal of physicists would be to say, no, the quantum mechanics is understood for many, many things, and here are the real problem, here are the things that we really do understand, while it's often said that we don't understand them.
The difficulty is that the language of quantum mechanics is a mathematical language, which is nearly impossible to be translated into ordinary language. So one has to find the equivalent in ordinary language of what we are doing and what we are understanding completely
Yeah,
when
that's
we are
true.
just making a calculation which will allow us to just account for some phenomena.
But yes, but the third question is what interpretive program can make the best sense of quantum mechanics? Is it just a set of rules, or is there something more? Or can we say that quantum mechanics is just a set of rules which help us to organize our knowledge and our view to see these phenomena at a microscopic scale, or is it more than that?
Okay. So that's the question, because I think that's a real question that one could ask about what is an interpretation. But what I wanted to say before that is that often when you read article for the general public or some discussion, one spoke about interpretation of quantum mechanics, and one makes a distinction between three different things, in my opinion. First, there are different formulations of quantum mechanics. For instance, the quantum mechanics that we learn in university or in grandes écoles, which you learn what is a wave function, what is interference, what is the duality particle and between wave and particles. So it's a mathematics, the way to formulate mathematically the theory. Then there is a problem of interpretation of this mathematical framework, which is the standard quantum theory. And then one often heard the name of Copenhagen interpretation or the many-word interpretation, and there are some more fancy interpretation like called modal interpretation. I don't know really what it is, but so there are many, there are a long list, and it's increasing every year, I think, of interpretation. And then there are alternate theories. And often one discusses, says, for instance, as a theory of hidden variables, I presume we are going to discuss that later, are interpretation of quantum mechanics. But I think, in my opinion, and in the opinion of many physicists and mathematicians, in fact, there are different theories in the sense that they are incompatible with quantum mechanics. So you have the quantum worlds, the worlds that we observe, we make experiments, we see atoms, we see light, we see waves, and we try to understand it. Then there is a very good physical theory that is quantum mechanics. And then there are alternate theories that gives different prediction, and that can be distinguished by experiment or by mathematical reasoning, looking for some contradiction. And this is all often mixed up and said under the name of interpretation of quantum mechanics.
I really thought myself that hidden variables or pilot waves were another interpretation of quantum mechanics, in the sense that they were still valid. Maybe it's a controversial.
Provided they give exactly the same answers.
But so far,
So far,
if they are non-local, hidden variable, it's what I heard is that it's still valid.
Yes.
No,
Well, there is a little subtle point, but so I think, that's a very technical point. But I think they are still incompatible because there is a problem called contextuality,
yes.
and the
Say a
hidden
bit more,
variables.
maybe just we get a bit technical, but what do you call contextuality?
I have not invented this term; it's very old.
Yeah.
Contextuality means that you can interpret you can explain by the same set of hidden variable or element of reality it's a term that was, I think, introduced by Albert Einstein. In terms of element of reality underlying the physical world that can explain all the incompatible measurements that you can make on a quantum system. And there are mathematical theorems that state that this is impossible. So in the sense, the element of reality you have to introduce to describe a quantum system depend on the set of measurements you are going to do on this system. And then you got into a lot of trouble. If the reality depends on what you intend to do as a measurement act, then I think for me it's a big problem. It's a much bigger problem than understanding non-locality or understanding entanglement. But that's my opinion.
Not quite the same, nearly the same, but if we just focus on the idea that interpretation is just a means of putting words on reality. Reality is somewhere, but we have to understand it. Understand means putting words, and now these words which we have, which we can use, our language is a language which has been built by our experience at our scale. So in a way, interpreting quantum mechanics is just looking at what can be said at our scale about phenomena which are at just a microscopic scale, which we cannot reach directly. So interpretation of quantum mechanics is something in this sense of interpretation. Then it is what can we say about a system? Now, what we can say about a system passes through an apparatus which is large, which has our scale, which we can read and so on. And interpretation, in the sense that I'm using it, means translation of what can be said about a system. Now, in this sense, contextuality just comes out by the fact that what we can say about a system passes through an apparatus, and if there are things about a system which is prepared in some way, an experiment which is done, and things which can be said with one apparatus and other things which can be said only with another apparatus, then contextuality means that the reality which we are checking through an apparatus and the reality we are checking with another apparatus, that we cannot put them together in words, because our words are related to our scale and to an apparatus which is at our scale. Do you agree?
Yes. Yeah, I would agree. Perhaps I may make a comment. It seems that your description of this feature of quantum mechanics goes back to Niels Bohr and this idea of complementarity.
Yes.
It's more precise. Is it a more precise way to formulate this complementarity principle of Bohr, or is it something different?
It is a more precise. It is a more how should I say, more realistic way, in the sense that maybe I say it this way: interpretation is something which emerges from an experiment. Mm-hmm. If you don't do an experiment, you cannot say anything. Things which are not tested experimentally, we cannot say anything about them. So if we need different experiments, each experiment will give us one aspect of reality through an inference. I will look at the apparatus, and looking at the apparatus will say, oh, it's this. So we say, oh, I have a theory, which means that if the apparatus says this, then I can say this thing about the system. Now I take another apparatus. This apparatus, I look at its answer, then I can say something else. But the else which I'm saying here, I cannot put it together, because yes, the interpretation I gave, this interpretation is not an interpretation of what happens at the microscopic scale. It's an interpretation which goes through the apparatus. And the advantage of studying models of measurements and making a theory of a measurement which itself must be a quantum system, and trying to make something coherent together with that is a way to understand what is meant by interpretation.
So for you, interpretation is not, you can dissociate an interpretation from the action of performing a measurement of interaction with the
Yes,
quantum system.
the interpretation is something which emerges in the sense of reduction, it emerges from a macroscopic process, a process of interaction between something at our scale, which is an apparatus, and the object. The apparatus which can register, which can print, and so on, the result. But what is printed is not the same reality as the macroscopic reality. It's just an image of this reality.
Okay, so this
and an image taken from one side is not the same as the image taken from another side.
So Roger, you made the perfect transition to question 4. So what are quantum states?
Quantum states, that's simple. Quantum states are mathematical objects which gather all information which allows me to make predictions, some prediction or some other prediction about a system. A state is not a property. A state is not a property of the system. The word state is very bad. The word state is just gives the feeling that it's a property of the system,
Of the microscopic,
of the microscopic
reality.
system.
Ah.
However, what we call a state, which is represented by density operator and so on, what we call a state actually is a kind of bookkeeping of all what we can say about a system, but not really about a system itself, but about all systems which are identical to that one, because physics deals with generic questions, not with individual objects. So a state doesn't belong to an individual object. A state is just it's a mathematical object which allows me to make predictions on a set of objects all prepared the same way. Would you agree?
Yeah, I think so. Perhaps I'm a bit more oriented to what one can say on a single quantum or a few quantum systems, but I would agree. I think that the quantum state is our best way to encode what we can say and what we know about a quantum system, but the information we can use to make manipulation on it. Manipulation may mean doing an experiment, doing observation, use this quantum system to encode information in quantum information science, but in any way it encodes the best we can know and we can do with a quantum system.
So for both of you, it doesn't have a deeper connection with microscopic reality, if we can.
Microscopic reality?
Microscopic.
Well, I think it defines, that's the best way we can speak about what we can put under the word reality in a quantum world.
Yes, you have this famous question between Bohr and Einstein. What are we describing? And Einstein wishes to see what is reality per se, but réalité en soi, per se, you say?
Réalité en soi.
Yes, réalité en soi, and this we can't reach it, and so I agree with Bohr's position. And Bohr said physics is about what we can say about systems and what we can predict about systems. This is the goal of physics, but the goal of physics, physics cannot succeed to say what is the deep nature of the objects which we are studying at the macroscopic scale. And in this sense, at least in this discussion between Einstein and Bohr, Bohr won.
So, and in fact, the question 5 is about, and 6 also, about probabilities and randomness in quantum mechanics, which is an interesting problem. And the question 5 is, does quantum mechanics imply irreducible randomness in nature? So
yes, so this question is very badly said. I would say quantum mechanics implies an irreducibly probabilistic nature of, not of nature, but of our description of nature. Our description of the nature must be irreducibly probabilistic because we cannot answer all questions at the same time, questions about incompatible quantities. But it is not nature which is irreducibly probabilistic, It is our description which is irresistibly probabilistic, and in a way that's obvious because probability is something which doesn't belong to nature. Probability is just a measure of our ignorance.
Yes, I would agree. I think that definitely quantum mechanics implies or is a way to formulate uncertainty in nature, which is a bit different from randomness. Uncertainty means that you cannot be sure of everything at the same time, which is a bit different and larger than randomness, which means that we see something evolving and being random. I think quantum mechanics really states that there is irreducible uncertainty, and some it manifests itself as randomness of quantum process. But I've not thought as much as Roger about what are probabilities and what is uncertainty and what is the measurement of ignorance. So I prefer to not say.
This is precisely the next question.
Yeah, the next question.
Oh,
So
yes.
probabilities, are they subjective or objective?
Now,
That's a good question, no?
There
This one.
is a book, I don't remember whose book, of probabilities, which says that there is as many interpretations of probabilities as individuals using probabilities. Now, just splitting probabilities as being subjective or objective is much too rough. Now, one extreme position is to say that probability is objective. Means what does subjective and objective mean? Now, objective probabilities, we could interpret them as saying that it is frequencies of occurrence, and this interpretation of probabilities, which are in quantum mechanics, this is an interpretation which can be given if you can perform an experiment many times, and if you can perform it many times, you will never get exactly the same result, but the various results which you obtain have some relative frequencies, and then this is one definition of probability. Now there is another definition of probability, which is a way of predicting something from a knowledge which we already have. So it's called Bayesian by many people. But then you have various types of positions about what does this probability mean. Now, in quantum mechanics, it's very clear in what it means. It means that you just assign some probability distribution by using the idea that you have a theory which you believe in, which is perfect, which is quantum mechanics. In quantum mechanics, you have a prior probability. What's important in probability theory is to start from something which is solid. Something which is solid is a prior probability. If you play cards, then you have a prior probability, which is that all permutations of the cards between the various players are equally probable. So this is the prior, and this is very important to have this prior. And then from that prior and from external knowledge, you can make predictions. So this is one type of subjective probability, which is perfectly sensible. Now there is another type of subjective probability, and unfortunately there are well-known physicists who just pushing their ideas in this direction, which is the truly subjective probabilities, in which case, so these don't apply to phenomena in which you don't know anything, economics, for instance, or rare earthquakes and so on, in which you have no experience, you have absolutely no prior, and prior probability is something which is left to subjective ideas, which means that you, looking at one phenomenon, you will attribute it one probability, and I will attribute it another probability, having exactly the same knowledge of the phenomenon. However, probabilities which are used in physics have a partly subjective aspect because they intend to predict phenomena. However, it is intersubjective, I would say. Intersubjective, meaning that all people having the same information must make the same predictions. Otherwise, it's not science. It is
that's important
it
point,
is
isn't it?
science. It is unfortunately there are many people who apply probability to domains, rare probabilities, for instance. Rare probabilities is something which has, in my opinion, absolutely no meaning. I have heard people who just attribute a probability to an earthquake of this size, an earthquake which takes place every two centuries. Attributing a probability to it is just, for me, a nonsense. And this is not what happens in quantum mechanics. In quantum mechanics, we have a prior, and we all, if we are facing one question, we are going to attribute the same probability. Of course, provided we have exactly the same information about this system.
François, do you agree?
I think, well, perhaps I agree too much with Roger for this debate, but I think that indeed quantum probability are rather objective. I still consider them that they have to be considered in this Bayesian sense of giving a precise mathematical definition of what we know about the system, what we can expect about it, but still they have to be objective in the sense that many different physicists or observer or quantum measurement of apparatus should, at the end of what they do, obtain the same number for the probability they assign to some event.
This is what I call
Yes.
intersubjective, because the word
Yes.
objective seems to mean that
Yes.
it's property
It's
of the object.
Yes,
It's
yes.
not a property of the
Yes,
object.
yes.
It's a probability of we all who are observing this.
Probably not specific to the application of probabilities to the quantum world. I think there is the same question and the same difference of point of view on what are probabilities and how to use them in the classical world,
Yes,
in
yes.
the quantum world, in physics, in economy, in sociology, climate science, pure mathematics.
No,
Anything.
fortunately,
Game theory.
Fortunately, in quantum mechanics, we have a prior. The prior is that there is an invariance, which is a unitary invariance, which plays exactly the same role as the
Yes.
invariance by permutations in game theory. In
Yes.
theory of games is perfectly sensible because there is this prior probability which
Yes.
is really sensible.
Yes, but perhaps one can.
Now, if you played with dice, and if these dice were systematically biased and heavy on one side and so on, applying probability would be just useless and not fruitful.
Yeah, but perhaps one should ask that those questions are still debated and important when one tries to apply quantum theory to quantum to cosmology or to quantum gravity, where which prior assigned to the wave function of the universe or objects like that are not still very well understood. It's an open question. So those questions are still have to be asked in some
Yes.
area of quantum physics.
Okay, so then let's move to the
Yes.
quantum measurement problem. Is it really a serious problem or just a false issue?
We have. I guess we have what is the measurement problem? The word measurement problem is used by people with many different meanings. The most deep meaning of measurement problem is the following: quantum theory deals with ensembles of systems. That is, we have a statistical ensemble, and we can make predictions on statistical ensembles with the tools of quantum mechanics. But these tools are not suited to describe individual systems. So, and the individual processes. Now, if I make an individual measurement, then this individual measurement gives some well-defined result. And of course, if I repeat the measurement, I'll obtain another one. But at each time, this result will be unique and well-defined. Now, the measurement problem we feel it, we see it with many other people as being the following one. How can we explain this property? By just treating the object which is tested and the apparatus which we use to test it, but as a unique quantum system. So we have a unique quantum system which has its own rules, and how come the rules of quantum mechanics applied to that have this remarkable property, remarkable from the viewpoint of quantum mechanics, not remarkable from the viewpoint of daily experience, because every day we know that when we do something it has one given result, but understanding this classical property from quantum mechanics. Now, what we have done during the last 10 years is to just elaborate a rather general theory, starting from models, and to, at least for ideal measurements, then the program is, I think it is solved. We can understand this uniqueness within quantum mechanics by just adding some small postulates.
Could you elaborate a little bit?
The point is the following. The point is that quantum mechanics allows you to show that a structure, if you take many measurements, now you can take the whole set of measurements and you can take subsets. Now the whole set of measurements and the subsets which you take, you can characterize them by weights, which have no interpretation directly in the strict framework of quantum mechanics, but which have exactly the same structure as ordinary probabilities, and therefore we can interpret them as ordinary probabilities. So ordinary probabilities emerge from quantum mechanics. In a way, I can make a comparison. This emergence is a bit of the same nature as the emergence of irreversibility. We know that if we take a classical gas, for instance, of particles, the laws, the microscopic laws are reversible, and there is no reason that at a microscopic scale we have a behavior in which we have a piece of gas which is hot, the other one which is cold. When we put them together, it becomes mild, but there is no reason that we have the inverse process. However, we observe the inverse process. So we have an emergence of irreversibility from reversibility, and here it's about the same. A measurement is an irreversible process in which, moreover, we have emergence not only of irreversibility, but we have also emergence of classical probabilities out of something which is the quantum formalism, which is not the same as classical probabilities. This is the way we think the measurement problem is solved. So the question was, is this a pseudo problem? No, it was not a pseudo problem. Are you blocked? Will it be blocked, and is it not solvable? No, it is solvable within quantum mechanics.
So I think rather than a problem, it's a question. Can we understand within quantum mechanics how the act of performing a measurement with a macroscopic apparatus, because all apparatus, including our eyes, our fingers that will touch something, are macroscopic objects. And I think this question has been started to be dealt as soon as quantum mechanics was created by Heisenberg, by John von Neumann. And I think now we have a pretty good idea, in particular by the recent work by Roger and Theo and his collaborators, that everything is compatible. We see that it is compatible, although the initial assumption of quantum mechanics that how observing a quantum system we get a definite answer that is, for instance, basically yes or no, or a particle is at this position, which seems a bit paradoxical. It turns out to be logically consistent with how quantum mechanics works. So in this sense, I don't think it's a roadblock. Problem might happen later if new experiments are performed and see that things do not happen as we expect from ordinary rules of quantum mechanics. But it's an important feature of quantum mechanics that we have to understand, and we start to understand quite precisely. But still, there are many, many interesting questions about how a quantum measurement apparatus works and what we can do out of these quantum measurements.
Yes, and one difficulty is that this apparatus is macroscopic, and therefore what we have to do is quantum statistical mechanics. And there is a social problem, which is that people who dealt initially with measurement problem were not really fond of quantum statistical mechanics. They believed in a quasi-mythical position of pure states, that is, of wave functions. So they try to analyze things always in terms of wave functions. And this, of course, doesn't fit with macroscopic objects.
Yes, that's true. But it's what one could say perhaps is that idea took time to permeate within the physics community, because after all, the scientists who first gave a coherent formulation of the problem of quantum measurement, or the question of quantum measurement, is John von Neumann, who is also one of the founders of quantum statistical mechanics.
Oh, no, he has that idea rather clear, but
Yes.
at that time, quantum statistical mechanics, he just founded it. He invented the entropy, for instance, but we needed lots of developments of showing how we can deal with a macroscopic apparatus within quantum statistical mechanics.
He moved too fast to other
Yes,
other
yes.
areas.
1930 was...
So this leads to the next question, number 8. What do the experimentally observed violations of Bell's inequality tell us about nature? No, Bell's inequalities.
So perhaps I can answer. So I think they just tell us that when you speak about locality and causality in physics, you must listen and write and read what Einstein did in 1905 and not what he did in 1935. So you have to take locality in the sense of Einstein and in special relativity, and
Locality, you mean?
locality, yes, and not in the sense of Einstein and John Bell. John Bell, in his very famous and interesting paper of 1933, I think, introduced a concept of locality that is much restricted than the concept of locality that is used in physics. He wanted to have locality with respect to some ideal hidden variable. And both the mathematics that were in fact existed prior to Bell's theorem and the mathematics that Bell used to show his famous theorem showed that this is incompatible with quantum mechanics. So, but this concept of locality is not the concept of locality that we used in high energy physics and that we have to use when we teach quantum.
So the difference is for Bell, he had this locality with respect to hidden variable as well.
Yes, he wanted to have hidden variables that were attached to part of of a quantum system, like having two photons. People are doing experiments now, having the photons carry independent element of reality. And we know that this is both not occurring in nature and mathematically inconsistent. So, trust the mathematics. When you think about quantum mechanics, trust the math and trust the experiments.
That's a good
And moreover, do not put together within the same logical argument results of experiments which are incompatible and which are made with different apparatuses. Because Bell's inequality, the paradox in Bell's inequality and in other similar paradoxes comes from the fact that you have one type of result which is made with one apparatus, another one which is made with another apparatus, you are not allowed to put them together. In the same way as if when you take a picture from this side and you take a picture from the other side, now in quantum mechanics you are not allowed to put these two pictures together to reconstruct the object from both sides.
Next question is about the foundations of quantum mechanics again. How can the foundations of quantum mechanics benefit from approaches that reconstruct quantum mechanics from fundamental principles? Can reconstruction reduce the need for interpretation?
I don't think quantum mechanics needs to be reconstructed. It's perfect as it is. Maybe some progress will come and we'll have to find deeper principles if we succeed one day to reconcile quantum mechanics with gravity, that is to have a new theory of space and time. But for the time being, quantum mechanics is our best theory, so reconstructing it is just a waste of time.
François?
Yes, I don't know exactly what reconstruction means, but I played a little bit with that game. But I think to reconstruct something, you first need to deconstruct it. And quantum mechanics, I don't think has been
There's no need. There is no need to deconstruct it.
Looking at trying to formulate the axiom of quantum mechanics starting from different point of view to reach the same theory as, for instance, people are trying to do in quantum information, trying to formulate the axiom of quantum mechanics from quantum information postulate, was saying with a quantum system we can manipulate information according to such and such law. That's an interesting point of view, but as far as I know, it always leads to the same quantum theory, which is quantum mechanics. So from that point of view, it's a different way to climb the same mountain. So it's interesting. We like to find new way to climb a mountain, but I agree with Roger. We definitely need something radically different, like quantum gravity, to have a new theory.
So then, if you could choose one experiment, this is the next question, regardless of its technical feasibility, to help answer a very important foundational question, what would it be? Do you have an idea?
I think the experiments which are being performed, in which these weak experiments, non-demolishing experiments, bring something interesting about the foundations, but simply they need to be explained by theory, which will not be so easy.
I think we should succeed in building microscopic black holes and see what happens if they really evaporates. What are the
So
quantum
who will
effects?
be the observer for this black
I
hole?
have to be a bit far away, but one has to be cautious, very cautious.
Or to observe the breakdown of quantum mechanics at a certain scale, no?
But to see whether it breaks down and what's really happening. Because after all, that's how quantum mechanics was created. That's because there were a lot of experiments doing with atoms, with radiation that couldn't be explained by classical physics. And quantum mechanics was invented and created by an interplay between theoretical idea, like the Bohr atom, and experiments. And often one forgets to, in the presentation of quantum mechanics, now we have reconstructed this story in a nice way and we present it in a logical way. But the way it happens in the 1920s and 10 and 20s up to the 30s, a lot of ideas were suggested by great mind and thrown out because there was just an experiment giving the opposite result.
Now
So I think we need experiments in quantum gravity, and that's much harder to do, of course.
Now, a few years ago, there were the hope that experiments would put a limit between a microscopic world in which quantum mechanics applied, and maybe quantum mechanics applies for objects which are complicated, a little more complicated, but as soon as you reach some size, then quantum mechanics breaks down and it's classical mechanics which takes place. There were some experiments, and it seems that there is no limit.
Yes.
A few years ago, we could think that maybe having an interference between a polymer and itself is something which is forbidden, but people have succeeded to let interfere large objects with themselves, which means that this limit, which would have been interesting from the foundational viewpoint, doesn't seem to exist, and quantum mechanics applies at all scales. So these experiments are okay.
There must be still
interesting.
classical limit at some point.
It's interesting. There is, in principle, there seems to be no limit.
Yes, I agree, but I think.
So what makes it like? Can you just for my own curiosity, what makes that some outcome of experiments are really classical and some?
No, but the people have succeeded to let interfere carbon 60 to
there are even bigger
itself,
molecules.
even bigger molecules, virus even.
Yes, we are excited because they say viruses are living things, but of course they are completely frozen in this experiment. But I would say that those experiments for me are very, very nice experiments, but they just confirm that quantum mechanics should apply to macroscopic objects, although it's very, very difficult and it's impossible to see quantum effects for macroscopic objects, or objects with 10 to the power 5 atoms or 10 to the power 6 atoms. But from the theoretical point of view, quantum mechanics says that nothing should happen and you should not reach any contradiction with what we observe in everyday life in the classical realm, what's called the classical realm of physics. So I expect more radical, but we need much more radical experiments to see something.
So maybe I just ask just a question for my own knowledge. So I don't get to, in some system we reach the classical limit after a certain size or whatever happens inside. And for some others, it seems that you can go as big as you. I mean, the size can increase almost up to infinity without reaching the classical limit. That's the point. So, what makes a difference between those systems? Or is it formulated correctly, or do you want something else?
The difference is which quantities you are testing. If for a large system, you cannot test all variables of the system. If you could test all variables of the system, then of course all that would be quantum mechanical. Since you can test only some macroscopic variables, these ones usually don't manifest when the system is large quantum properties, but they may.
So what would be all variables of a system? All variables of all the microscopic elements of the system?
Yes, if you could test them, of course, then you would test quantum mechanics at any scale.
Okay. That's okay. So the question number 12. If you have a preferred interpretation of quantum mechanics, what would it take to make you switch sides? François or Roger? François?
I don't know, because I'm not sure I have a preferred interpretation in the sense of just viewing the quantum formalism that we manipulate. But I would say either a new idea or new experimental results. But I don't know which one. So I think definitely if there are some experimental results that disagree with quantum mechanics, then you have to change our point of view on quantum mechanics itself. Otherwise, I'm not too worried about if someday I change my point of view of quantum mechanics.
Do you have a preferred interpretation or not?
I would say I mostly agree with the point of view of which is often denoted, but it's a bit caricature as a Copenhagen point of view, although it was never stated by Niels Bohr in the way it is often presented. But the standard way of viewing quantum mechanics as a way to make predictions on quantum system and use them and understanding the best what we can do out of quantum system so it's often called the operational point of view, is I think my preferred interpretation.
But it's just a matter of preference. If you had to work with another interpretation, you'd be happy.
Well, I think as long as I'm still using the equation of quantum mechanics and don't disagree with them, it's a matter of preference. But if someday I just say no, but it can be true, I can't believe that, then I will be in a troubled state of mind.
Do you think this day will come?
Well, perhaps, who knows?
Okay.
I'm getting old, so my state of mind changes less often.
I would say there is no real interpretation of quantum. There is a formulation of quantum mechanics.
Yes.
There are different formulations, but we know that mathematically they are completely equivalent. However, these formulations have in common one thing, which is that they are statistical, and that they deal about ensembles of statistical ensembles of similar objects. So this is the general formulation. Then interpretation is something which comes out for each given experiment. Then you can interpret it in terms of ordinary language. Now to change, probably it's quantum gravity, if someday it comes out, which will change things, because then we'll have to change our ideas about what is time, what is space, and so on.
And, actually, the question 13 is a little bit related to that. It's not really a scientific question. It's how do personal beliefs and values, whatever it means, influence one's choice of interpretation. So I guess the author had in mind if you believe in God or not, does it influence your view of quantum mechanics? That's the hidden question, I guess.
Yes, it's mathematicians, for instance, are idealist most often, and not materialist, because they believe that there is a kind of
mathematicians,
God.
you say?
There is because there is a kind of God which is below the nature, below matter, and this God is mathematics. So, in some sense, idealism leads people to believe that one could explain things, les choses en soi, per se. Whereas when you are materialist, then you don't believe that there is anything transcendent. So in that case, you are rather modest, and you believe that science is to try to dig our hole and to understand things, understand with our poor language, with our poor way of seeing things. We build mathematics to understand things, but mathematics don't exist outside ourselves when you are material. So this makes a difference. And if you are materialistic, then you are more modest than when you are idealist. Einstein versus Bohr.
François?
Well, it's a personal question. I'm not sure I am a deep thinker enough, deep enough to give a good answer. I think they both influence, because when I think about quantum physics, I have a tendency to change my mind about some other opinion I have about, for instance, the difference between idealism and what you call materialism, but that I think is more often denoted as pragmatism in philosophy. And so they both, it's part of life, and both influence each other.
So
I'm not sure I can say more.
Just a small question between the two of you. Between Einstein and Bohr, which one would be the idealist and which one would
Einstein, of course.
Yes, and the pragmatist is Bohr.
Yes, of course. And this question is also at the root of this old debate about why is mathematics so well fitted to physics. So it's this old question. It's a kind of miracle. Where does this miracle come from? So some answers are, okay, the miracle comes from the fact that mathematics is the essence of matter, and matter comes out of mathematics in a way.
So it's a kind of Pythagorean.
Yeah, yeah, pretty
Pythagorean.
much,
And,
yes.
if you look at people like, comment il s'appelait, une catastrophe.
Tom.
Tom,
Yes,
yes, Tom had exactly that viewpoint.
Yes.
But physicists usually don't have this viewpoint. And my own answer to this old question is that physics and mathematics develop more or less in parallel, and physics benefits from the progresses of mathematics, and conversely mathematics develops at places where physics brings them questions. So this convergence between mathematics and physics is just the result of the evolution parallel of
It's a
physics.
co-evolution.
It's a co-evolution, it's a symbiosis of mathematics, physics. But this is not at all the only answer. So a lot of people believe that many other answers. So philosophical positions just have an influence there.
Yes.
So question number 14 is a bit related. What is the role of philosophy, if any, in advancing our understanding of the foundations of quantum mechanics?
Yes, this question I would set in the other way. Understanding foundations of quantum mechanics just gives us some way of understanding, of making good philosophy. Making philosophy out of science is not fruitful in this domain. Epistemology is something which comes out from science.
Yeah, I'm not a philosopher, so I'm not sure I will give a sensible answer. I think perhaps, at least, my impression is that when quantum mechanics was invented by very young physicists, many of them had a much better culture in philosophy than we have now, and it helps them to get rid of the misconception about classical physics, for some of them. But so we should use philosophy as a way to get rid of old ideas.
So next question, where would you put your money when it comes to predicting the next major development in the foundations of quantum mechanics?
Unfortunately, I have no money to put in that. But it was also already said in quantum gravity.
Yeah, I would say to quantum gravity.
So we are at the last question of this this little interview. What single question, so it's a typical question, about the foundation of quantum mechanics would you put to a omniscient being, whatever it means?
It's a
Questions about foundations.
Mm.
Yes, like do you play dice or something like that, or
So, see, it's a bit of a joke, so I have prepared an answer that is also a joke, which is, if the world is quantum, how do you know you are omniscient? Which is but I think it's a question about the foundation. It's a bit of a joke, but...
so.
And you?
No, I don't know what omniscient means.
Yes, that's what I mean.